Do you see my screen?
Yep.
Okay, cool.
Yeah, so this is a continuation of the final project for 2020 Formula One Trent Autonomous Racing, and so we are at Team 5.
Hey everyone, my name is Payman, and I'm here with
Actually,
Christopher.
we can't see
Sorry.
it now. I think you have two monitors. That's my guess.
No, I only have one. 1 second. Do you
It's good
see
now.
anything
Just
now?
focus.
Now it's
Yeah,
good.
it's good.
Maybe like this is it?
Yeah. Now we're good.
Yeah, I was just presenting to myself. Okay, so my name is Payman. I'm here with Christopher and Yue to talk about our project. I know that we're the last team, so by now probably a lot of people are tired of different methods, so I'll try to be more exciting so that we all like it. Starting, our approach was kind of different to the previous 4 teams in the way we approach this problem. We kind of got into this conclusion by talking to the instructors, especially Matt, that one of the big components of this project is going to be prediction. So most of our work has been on how to make sure our predictions are better and how to make better decisions at each time step, and also have safety as a concern while we're making those decisions. So we try to kind of combine some of the formal methods or some of the methods that have more guarantees in terms of performance with learning-based methods to kind of get the best of 2 worlds and perform better than maybe just using those formal methods by themselves. We decided to come up with a couple of spline packs that cover all of the race. In this way, we could have kind of posed this problem in a way that we can learn. We decided this way because then we have a fixed amount of action space that we could have, and then using those action space, using those paths to make decisions, and then go from there. The RL is going to have the high level decision making, and we're going to go over that later in the presentation. This is just an overall view. And then we use just pure pursuit and kind of time to collusion method to decide if that decision that the RL made was a good decision or not. And if it is, we use pure pursuit to follow that decision. So this is the overall structure of our approach. We created 17 paths. From those 17 paths, 16 of them cover the whole map, kind of uniformly. And then one is a really optimized path. When I say optimized, it's not really optimized for speed or time. It's optimized for distance. So we're just trying to make sure it's a path that goes around the shortest distance, and it's also safe. So, and then the other thing that we did is that we use RL to kind of understand the environment better when making decisions. And our approach kind of works this way, that we have a train policy. Using that train policy, we get an action. An action will be one of those paths, which path we should follow. And then that path or that decision goes to a check, kind of, and to check if the path that we decided is available or is a good path to go. And that's based on a set threshold we have for TTC. We have time to collision for that direction. We check if going that direction is a good idea, if it's safe or not. And if it is safe, we do follow that path using pure pursuit. And if it's not safe, we have like a side TTC algorithm that takes over and makes new decisions just to make sure we don't collide with a different car or with the car in front of us. So the RL makes most of the decisions, but at the same time, we have a backup plan in case the decision that the RL made wasn't a feasible or a good decision. So you can see our path here.
We interrupt you. Could you share your full screen, because it looks like you're just sharing part of it.
Sorry.
Like when you share with Google,
yeah, sure.
you share with the so it looks like somehow it's cropped.
Do you see the whole screen now?
Yeah, I see your whole.
Well,
is it good now?
Are you on your iPad?
No, I'm on iMac. I'm not sure if Macs are.
It's very narrow.
Okay. Let's see. Is it better now?
Yeah. Go ahead.
Is it good now?
Except for is it good? We're just seeing gray black right now.
I'm not sure what. Maybe I should stop
go to
sharing
presenter
again.
mode.
Let me see.
Presenter mode. It was, yeah. Oh, it was good for a second. Yep.
Is it good now?
Yeah, it's much better. Thank you.
Okay.
All right, cool. Yeah, sorry. Haven't done that in a while. Okay, so let's go back. So yeah, you can see our paths here. They cover the whole map. And we use B-spline to get them. We didn't really do anything fancy on creating these paths. Just found the waypoints and then just use B-spline to get, and it's just pretty much the paths are just waypoints. So we don't really need to do much about anything else. And then we have one additional path that is not shown here. And that is the path that is the shortest distance around the track. And our hope was that using that, we would be able to kind of help the RL approach to kind of use or choose that path when available or when we can, because that kind of has a guarantee to be pretty fast. So you can see, so this is our TTC algorithm, I would say, that we kind of like jumble together a mix of different things. And the idea is how to make like fast decisions and also be safe at the same time. So we start with the path we are at. So when we initialize a specific path, and then in that path, we find a waypoint. Using that waypoint, we check in that direction of the path if the path is safe. If it's not safe, we decide to change lane. And if we want to change lane, then we check for all paths to see which one of the paths around us is safe. And we choose the path that has the highest time to collision and repeat the process again. So we continue on a path that is safe unless it really isn't safe, and then we decide the least dangerous path to follow.
Yeah, okay. So so when we wait, can you go back a slide? Just real
sure.
quick. So basically, when we're doing this, you're basically finding the paths that are like really available to you. And from that, you get a set of available paths out of the 16 or 17 available 17 paths. So you get a smaller set, and then we feed it into RL. So you can go to the next slide. So when you get the observation, so our observation, we'll define it a little bit more later, but we get an observation of LiDAR ranges and opponent observations and things of that nature. But we set it to be a size of 256, and we feed it into 2 Q networks, which each have this same structure with 256, 256, 128, and then outputs a discrete action set of 17 actions. And this is based on whichever path the RL wants us to take. And then from there, you sum up the 2 Q values. You sum up to the two Q values, and then these you can. So after you have the set of 17 Q values, you do the softmax to find the probabilities of this, and then from there you can take an argmax to find which action you should take. And then our SQM policy was built on soft actor critic from Spinning Up. And I built it based on Clip Double Q learning from Fujimoto in 2018. And it converts it from a continuous action to discrete actions, and then uses entropy regularized exploration. Next slide. So the main part about SQN is the use of entropy regularized exploration. So this is basically when you're exploring the space in the beginning of training, you want to increase the amount of entropy you have in the system, and you can do this by using this kind of formulation we have here with in the first line. And the alpha is basically a temperature term that you can tune. It's a hyperparameter you can tune to control how much entropy you want in the system. And basically, yeah, so then from there, okay, in the previous slide, I said we use the softmax and then take the an argmax to find a deterministic action at that spot. But during exploration, what you actually do is you take that those probabilities that you found, and you use those logits to create like a kind of a multinomial distribution. And then from there, you can sample from that distribution to get a more entropy regularized action rather than the deterministic action, which is the highest value Q value at that step. But then in the end, what you're doing is you're minimizing this WQ learning loss function, which is shown in the bottom line, where the loss is basically a difference between the Q function and the target Q function, which is something you could read about in WQ learning. And then, yeah, so you're trying to minimize this loss. And yeah, as that question I just saw, yeah, it's different than epsilon greedy. So epsilon greedy, basically, it's you reduce. So at the beginning, you're basically taking fully random actions, and then you decrease epsilon as you go through training. But where this goes into play is that you do the same thing in the beginning, is where you do like a set amount of start steps where actions are fully random, but then rather than taking the deterministic action at a certain space, you take rather a sample of a sample from that distribution, that Q value distribution. So it allows you to sample the not always, you don't always take the highest valued Q value as your action, but sometimes you take a lower valued Q value so that you explore the other actions more, and then you have a better understanding of, I guess, the state space that you're learning. Okay, you can continue. So together, so once you have this full setup, what I did was at first I trained the ego agent against the pure pursuit agent that just basically drives around the original one. And what I found was it didn't really learn, what I realized, it didn't really learn anything that special, because it kind of learned where this opponent agent would always be. And then kind of just, it knew that at a certain point, it would just basically need to just get around it at that, because it had the same path every single time. So it just learned to overtake it at that specific moment. So instead, I trained it on an agent that followed a single path with TTC reaction, so that I can get an agent that had a more reaction, so like a more reactionary thing. And then when I trained that agent on our ego agent on that opponent agent, I then fed that same policy back into I made that the opponent agent, and I retrained it again. And you can continue this iterative policy iteration essentially over the new opponents on more and more tougher opponents. And then also some side things I did during training was I used the cosine learning rate schedule. So I started at like 0.01 learning rate, and I decayed it to 1 to the -5th power learning rate. Another thing is that since our starting initialization will be changing whether you're in the first position or second position, I randomly initialize the start at every episode so that the agent would learn that there are different possibilities for starts. The next thing I did was, so there's also target networks that you can look at for double Q learning, and I update this with Polyak averaging. And then finally, the policies that I've been choosing as the best policy during a training process was the one with the best online episode test return with deterministic action. So every epoch we do 10 evaluation tests, and we see the average episode return from that evaluation set, and then report it. So then what we choose is the best, the policy that gave us the best evaluation set answer. Okay, next.
Okay, and I will introduce more details about how we modified our reinforcement learning definitions to our case. Firstly, we set the gene environment. We modify the gene file with the observation states, the action dimensions, and our reward functions. And in order to include the map environment, we add the map configurations and the image files to it. And second, for our race agents, we have two agents, the eagle and the opponent agents. Both can use the TTC obstacles avoidance strategies on all the possible paths, and we create before. And actually, we have different strategies has discussed before, and we can also use the pure pursuit to follow the waypoints. Next slide. Payment. Okay. For our observation state, we converted it into the observational ring. Their first step, we subsampled the laser scan range and got the information, the orientation, and the velocity of the opponent card respect to our card. And also we find our distance to each pass we produce before and including the optimal one for it. And for the action space, as discussed before, we have 17 possible actions related to the 17 possible passes. Last slide. Okay. For our case, we consider the collection check and the number of laps in the process as the reward functions. For each time step, firstly, we check the collections. If we observe the collection, and we will decrease the reward. And for the first laps of our cars, we set the minimum time. We set the minimum time step. The time step is equal to the 0.01 as the reward. And then for every time step, it gets more rewards if the car win the loop. So we increase it as the lap time differences of the two agents. Okay.
Yeah, so what we can see here is that when you see the GIF go back to the beginning, the agent generally chooses the optimal path, which we learned is like what we just set as like pretty much the shortest path we can find from milestone 2. And then it uses TTC if it sees the opponent car like right close to it or any obstacles, and it avoids it. And then on the right, we can see the evaluation graph that I was mentioning that I used to choose the policy to use in the future. And then at first you see it starts off pretty low, where negative 100 means that a crash occurred, and then all going up so like every time step you get negative 0.01. So then a longer race means that you have a more negative value. And then you can see, so the main reason we use this this kind of setup also is, and the reason a lot of people want to use RL for control is that it is very efficient to execute online. And you can see this by our drive topic rate is over 200 hertz with all this together. And we don't have to do like asynchronous time steps or anything like that. This is all fully calculated every time step. So it's extremely efficient. We can go next one. Some possible things we can improve are like including more lidar information. Right now we're only using, so we subsample the 1,000 lidar steps into like 200-ish lidar ranges, equal sampling. And then another thing we could do is, instead of pure pursuit, we can use MPC to do a better path following planner. Another thing is, so like every single time I was doing this like iterative self play, I was relearning the policy from basically nothing and having to relearn the entire model again. So I think another better thing would be to use like kind of a prior model for learning, so that the agent doesn't have to relearn everything, but it can start from some baseline prior. Another thing is we can add more paths or a better optimal path using like, I guess the path optimization thing. And then since we're also using only B splines, we could use cubic splines to optimize for better velocity. And then finally, we can also consider the opponent predictions, like where they might be in the future. And so we can include that into the state. But yeah, these are all possible future improvements to our algorithm. Yeah. Oh, thank you. I think that's it.
Thanks. You guys have any questions?
You guys are very popular, lots of questions. So maybe y'all can pick from, what are the top questions that you have here. Y'all answered quite a few on, but you can also talk about them over here.
Yeah, I guess we can start with, I think I should go over the overall algorithm again, because basically in the beginning, you have the full 16 paths and the 17th path, optimal path. And what you do is you're using TTC, well, you use kind of like a preliminary TTC calculation to see which paths are available to you from your current location. So like, say you're in path 7, the only paths available to you are probably like 3 to 10, because path 15 is going to be very far away from you. So our path selection is already reduced. From there, it's fed into RL so that the RL can choose which of those subset of paths are available to us. And this is done by masking out the actions that are not possible in the action selector. So the argmax doesn't choose the paths that are not available. So then when SQN chooses the path and it outputs a path, now the card looks at that path and calculates another TTC on that path waypoint, and sees if this TTC is below a certain threshold that we set, then now you need to do TTC. If that waypoint is fine and it doesn't violate the TTC constraint, then you just do normal pure pursuit to that path. So if we do see that the path that RL chose violates TTC, basically then you go back to that set of available paths that we found previously, and we calculate the TTC of all those paths. And then from there, what you do is you take the path with the largest TTC time, which means that there's the most space in between, and then you follow that path. And then we follow this iteration over and over again.
Also, we combine one other thing to this, is that when we check for TTC, it's kind of a mix of reactive method and previous steps. When we look in that direction, if we find an obstacle that is really close to us, we widen our horizon to look more widely for that specific path. So we find all the possible close edges that could be in that direction.
Yeah. Other questions are, did you use the rollouts using Gym Simulator? Yeah, so we use the F1. I modified the F110 Gym Simulator, and I added, I used that and I put it into the spinning up kind of repo, and I made SQN and I combined. So I basically used, and then we added a bunch of like the reward definitions and observation definitions. TTC safety checks. So like if there's no paths available to you at a certain spot, then we just stop basically, and then that's it. If TTC is very close, if the obstacle is very close and TTC is very low, then we use a safe speed, and then hopefully we can find a better path to go from there. Do people ever use RL for control as opposed to planning? So like for my thesis, the main thing is for using RL is like you use a really large extended training stage so that you can learn a very efficient policy that can execute online, as shown by our very high frequency rate, calculation rate. And do we consider using different inputs like occupancy grid instead of scans? So we did consider using like a global map as our input. So like we could probably use like an occupancy grid on a global map, and then use that input use it as an input image into the RL algorithm. But with images, the problem with images is that they're very large input sizes. So you need to use a GPU, and we felt it would just be faster and start simpler to do just a normal multi-layer perceptron with value, like just a vector input.
Also, like I don't think it would have made a huge difference in terms of performance. It wouldn't be additional. Yeah.
Right. Reframing the question, how is it declared RL passed or failed? What does that mean?
So I think one thing is that we also mask some of the paths when
Oh, yeah.
RL is making a decision. I think Chris mentioned that, but just to reiterate, when we're making the decision, we do check which paths are available, and we do check their CPC. And if it's a really bad path, we kind of mask it out, so we don't choose that in training. And to declare if a path is bad, I mean, it's really hard to decide that. While you're training, you crash or you make a decision that your reward is going to be bad. But in tests, a bad path, it's kind of subjective in a sense. But at the same time, for us, bad path will be a collusion. So that's why the only time that we are making, like, we're sure that it's a bad decision is when we're going to go in a direction that we're going to collide with something. In that case, then we take over. But in other cases, we don't try to mess up like the decision it makes, because that was the whole purpose of learning, to be able to predict and then make decisions that we wouldn't be able to predict ourselves.
Yeah, exactly. So like someone asked, Samya asked if we incorporate prediction, and we don't like specifically incorporate prediction, but we feel like, yeah, it's kind of like a black box, and over time with enough interactions with the opponent agents, you should learn some of their tendencies. Like that's why I said when I first trained it on a pure pursuit agent with no reaction, like no reactionary kind of things, the agent basically learned where at what point it would be able to catch up to the pure pursuit agent and overtake it. And it just learned that it didn't matter like what was happening in the map. It just would always decide that it would do like an outside wrap around overtake. And then so when I gave it more of a other opponent agents that have more reactions, it kind of learned that the opponent agent would react to it being there. And I feel like it does push away, like it does kind of learn to take the inside loop and push away the opponent agents, because I think a lot of other reactionary methods are going to try to avoid all obstacles. So by taking advantage of this, the RL learned that if it kind of squeezed itself in a little bit, it would be able to find a way through. Do you think of online fine tuning of the Q network during race to learn better?
It would be hard to learn. Like, yeah, it would be hard to learn in a race setting.
Few shot learning.
Yeah, we didn't really think of that approach.
Yeah, that's what I was saying. Like instead of retraining every time on the new policy that was learned, like when you gave the new policy learned to the opponent to learn off it, I think it would be better to use kind of like a prior policy as your start, and then use like few shot learning, or well, basically few shot learning is just retraining again on the same policy. So like, yeah, basically use the old policy to retrain on a more difficult agent, and then keep training on that same policy. So yeah, basically transfer old network. Mm-hmm. Yeah, I didn't do that, but yeah, that's definitely something that would definitely help the training. But also it could end up in a policy that might not be, well, it's probably biased towards a certain policy. So I think exploration would be kind of thrown out the window, but
I think one of the biggest thing that made it, like, I wouldn't say easy, but made it possible for us to learn and perform, like, I would say decently well, is the way we framed the problem in a way. The way we decided to go with paths, the way we decided to cover the map. Like, I think all those decisions to frame it in a way that is learnable, or is easier learnable, kind of made it easier for both for debugging, so we would know exactly like when a decision is bad, and also for learning, because then you have like a discrete amount of actions you could take, and it will be a lot more stable also because you have a fixed path and you wouldn't be changing directions all the time. So I think the framing was one of the reasons that it performed decently well.
Yeah, I agree, because with these set paths in pure pursuit, it's actually quite difficult to crash if there's no obstacles or anything, because our pure pursuit tracks quite well, at least in the simulator. And then so as long as you're following a path that's available, yeah, you really shouldn't crash. So I felt like what it did, it allowed the agent to not have to learn how to drive, but rather which paths are the best, and also how to use the paths to beat the opponent agent, like how to overtake or anything like that. maybe
Yeah,
block.
exactly.
Yeah.
So one thing that I think maybe wasn't addressed that we found in a paper that Billy and I wrote is that the noise in the real life LiDAR is more of a problem than you would expect when transferring the policy from the simulator to the real world.
Mhm.
So, for example, you know that part of the track is like by the doors of Skirkinich with the glass and metal plates. The LiDAR readings go haywire there. Did you guys try adding noise to the LiDAR during training, or
No.
something to sort of think about in the future?
No, we didn't.
Yeah, we
Also-
shouldn't, but I think we should have. We should have done that. I think we kind of decided to make this. Obviously, there will be some more decisions we would have made if we would have actually put this in a real car. That probably would have been one. But I think we kind of used the structure of the problem also as a way to
Take advantage,
set up
really.
take advantage,
Yeah, kinda
or
take
like
advantage,
or
yeah.
like take the setup. So yeah, some of the decisions may not be the best, and you probably would make a different decision if this was actually happening in real life.
I mean, I think it's also interesting to consider, like, if you can localize, right, and then you're using the grid, the off-grid image as your input,
Mhm.
that would be more robust to LiDAR noise because you're getting the off-grid partially from the map prior.
Yeah,
So it
I think
wouldn't
that
be so
yeah,
sensitive to the vector values that you get from like a single return.
Yeah,
yeah, I definitely
we had a
agree
lot
with that.
more. We had a lot of ideas on how to decide the observation state or like what to feed in. We kind of did go with a simpler version of whatever we were trying to do. We had like a lot more ideas and things in our mind. I think one of the reasons when with the decisions we made were time constrained at the same time, because making all this work and make it work fast, it was kind of not easy. But if this project was a longer project, then I think we would have been able to do a lot more in terms of like what to feed in,
Yeah.
improve the actual structure. There were a lot of things we could have actually improved that made this a lot better.
Yeah, especially if we actually had to do this on the real car. I think some of our decisions would have had to change because, yeah, we didn't have to consider all the noise and stuff, especially since RL, I'm pretty sure we've pretty much overfitted to every opponent agent that we've learned against. So like basically we need to do better ways of generalizing to different tasks. Like it would have been great if we had one of the other team's opponents to train against, because that definitely would have improved things. Probably would improve things, but
Yeah. So, yeah, I totally agree with the decision to keep it simple. I think maybe to sum things up, like we've had 5 talks now. I think some of the things that maybe we've learned from the project are, one, using a model predictive controller with the proper linearization formulated as a QP is great for path tracking, and it's extremely fast. I think we've seen a couple people try that, and it's been mostly success. I think we've also learned that it's important to consider sort of the software architecture of your agent. That's separating the concern of planning and control, especially when you have something more heavy duty running in the planning, is important. Planning slower is almost like it's the whole planning fallacy in action, right? By the time you come up with the optimal thing to do, it's no longer optimal because something else is happening in the world. So I was happy to see that multiple teams found that issue and addressed it. I think the other thread that I've seen amongst all the projects is this idea of discretizing sort of the action space, whether it be via quote lanes or offsets or even Project 5. You know, this idea, I saw it last semester and I'm seeing it again this semester, and it's been pretty successful. So I think it's sort of attacking the planning problem and trying to make it similar. Instead of searching for trajectories online, you just have a bunch of different options that you pre-computed when you had time before the race started. So overall, I was really impressed with the projects and also the variety of approaches that even within a single team were tried. And I guess I'd like everybody to maybe unmute and say thank you to Billy for just working endlessly to get the simulator ready for you guys. I take basically no credit for that. Billy has been not sleeping for a
Thanks, Billy.
while, and
Yeah, thank you, Billy.
without him, this
Thank you,
Yeah,
Billy.
when you
wouldn't go
fucked it
so
up
well.
really good.
Thank
Thanks,
you.
Billy.
No
Thanks,
problem.
Billy.
Thank you.
Any other closing thoughts from the teams or suggestions? So I think